Today I'll be teaching combinations and permutations, and I'm actually going to teach the next two classes since I'm going to be traveling during the last class. So I hope you enjoy today's class. Okay. So we're going to go over what permutations and combinations are. Perhaps you may or may not have heard of them, and there are two very important ways to count in math. So a permutation is an arrangement or listing of things in which order is important, such as if you take numbers 1, 2, 3, and if you arrange them in another way, such as 3, 1, 2, that's two different examples. While a combination is an arrangement or listing of things in which order is not important. In this case, if we take 1, 2, 3 or 3, 2, 1, that set, it's the same combination since they consist of the same numbers. And the symbol, exclamation point, is pronounced factorial, and it's defined as follows. Actually, in general, n factorial is equal to the product of the positive integers 1 through n. And here lists the values for 1 through 6. And we don't have to memorize them, but after a while, if you get used to using them in problems, naturally come. And also, we define 0 factorial equals 1. And later, it'll be clear why it is the case in many counting problems, or if we continue the study of math. And there is the product rule. That's a fundamental counting principle. When a task consists of k separate parts, if the first part can be done in n1 ways, the second part can be done in n2 ways, and so on through the kth part, which can be done in nk ways, then the total number of possible results for completing the task.
I have a question.
Yeah.
So what are those numbers, those small numbers below the base mean?
These?
Yeah.
Oh, that's just if we divide the task, we classify them as n something, we classify that as n number for categories. For example, all of the tasks of n1 are indistinguishable, and all of them for n2 are indistinguishable, and so on. Is that good?
So, and for the number of ways.
For the number of ways. Yeah, actually, that's a number of ways, but this category, it's some ways. For example, you could look at a problem. For example, if a designer has 3 fabric colors, he may use for a dress, and 4 different patterns are available. So then, in that case, N1 is 3 and N2 is 4. I think that'll be more clear after we look at a problem. But in general, if it can be done in n k ways, then the total possible results for completing the task is given by this product. You multiply each term from n1 all the way through nk. That can be explained using a tree diagram. Here, if you look for this problem, so in this case, n1 is equal to 3 because there's 3 fabric colors here. And there's also, it says 4 different patterns are available for the dress. So N2 is 4. And if each dress design requires 1 color and 1 pattern, how many different dress designs are possible?
12.
Yeah, because there's N2 ways. So it's 3 times 4 because you choose 1 and then there's out of 3 and then there's 4 ways each. Now, let's try another problem. We're going to look at the next problem. The girl has 5 shirts, 4 skirts, and 3 pairs of shoes. Okay, so Yo-Yo, do you want to explain?
So there's 5 shirt choices, 4 skirt choices, and 3 pairs of shoes that she can choose from, which means that the number of choices she can make is 5 times 4 times 3, which is 60.
Yeah, exactly. Because we have N1 equals 5, N2 is 4, and 3 is 3. So there's 5 times 4 times 3. And then we're gonna talk about permutations. So permutations are different elements with no repetition. Take R elements each time from n distinct elements, where R is between 1 and n. And then the number of permutations, P and R, is equal to factorial over n minus R factorial. This equation, although it seems a bit daunting, it's actually just you take the product from descending from n, there's some factors all the way to n plus 1 minus k. And in all, that's for n plus 1 minus r. In this case, in all, there's r factors. And this makes sense, since if you want to arrange r elements from n, then the first spot where there's r spots in all has n choices out of these n objects. And the second spot, there's n minus 1, since you already took 1 out. And then each new time you multiply, it's 1 object less. Now there's r spots. And n distinct objects can be permuted in n factorial permutations. That's a special case of P and R, where it's P and n. That makes sense because then you just choose all of the n objects to go into n spots. And you start the first time you choose n, and so on to the last time you only have 1 choice left. And letting n equals r in 1 gives us p and n equals n factorial. How many ways can the letters of the word math be arranged? Okay, so it's just math. There's 4 lectures, and then that's P44, which is 4 factorial. So that's 24. Unlike permutations, combinations are used when order does not matter. If we have n different elements and it does not matter which order we take the elements, the number of ways to take m elements where m is strictly between 1 and n is n choose m. And letting n and r be non-active integers such that R is strictly between 0 and n, then
what are some examples of R?
R, we'll see soon in this part. R could be, for example, 0, 1, or n, which are common.
Wait, so that in a problem, how will we know which one is R?
R, so it's basically in n, given n objects, how many ways are there to choose R objects out of them, where order does not matter. For instance, if you want to choose from 1, 2, 3, 4, 5, if you want to choose 1, 2, 3, that's a combination. And 1, 3, 5 is also a combination.
Wait, so it's the number of choices you can get from n?
Yeah.
Okay, thanks.
No problem. So when we let NR be non-negative integers, and this is read as n choose R, that's defined by n choose R equals PNR over PRR. So this you could derive by first multiplying both sides by PRR. And then you could see why that holds. Because if you pick first from n elements, you pick R of them where order does not matter. Let's see NR. And then out of each grouping of R, you could arrange them in PRR ways. And in all, that's P and R. So then if you divide, you get this equation. And that, plugging in the formula for P and R and PRR, you will get this equation. Since this part equals PNR and R factorial is PRR.
Wait, so like if there's a large amount of numbers for n, then how are we supposed to like just find R and plug it in? Can you give an example?
Sure. We could use this example here. It's kind of big numbers, but we just need the formula for it. So I could then go over it. In all, there are 15 animals.
Wait, is R in this case 6?
Right.
Oh, nice.
Good. So as I just said, remember, these are common combinations. N choose 0 is 1, N choose 1 is N, N choose N is 1. These you could also think they're kind of obvious, but you could also plug them into this equation and it'll always give those values. And since N minus N minus R equals R, we have N choose R equals N choose N minus R. since we use this equation, you'll get that. And those are the same, except the denominators are reversed commutatively. Yeah. So looking at this problem again, you could see, as I said, there were 15 animals and you have to choose 6 out of them. So it's C 15(6), which actually you could also write it as 15 choose 6, because in general, C and choose R is a lot of times written, especially in competitions, as and choose R, like that.
For this problem, do you suggest the formula or the other way?
Usually, well, here I'll usually write it like this, since it's easier to write it in digitally, but usually you'll see it a lot written like this form. But you don't have to worry about it too much here.
Wait, but are we going to write like that form, or are we just going to write the answer?
We could write, usually for homework, we write the number, but for this problem, since it's a big value, we just need to find the formula. So can anyone give me the formula using this?
Sure. 15 factorial over 6 factorial times 15 minus 6 factorial. So you'll get, you could cancel 6 factorial with 15 factorial. So you get 15 times 14 times 13 times 12 times 11 times 10 times and all the way to times 7. And then that is over 9 factorial. And then you can cancel, I think.
Yeah.
You can keep on canceling until you get the answer.
That's good. Very good job. So we're going to talk about grouping next. By the way, I'm sorry, first I have to erase some things from another class. And in the meantime, you could review about permutations and combinations. Okay, grouping. Let there be R types of objects, N1 of type 1, N2 of type 2, etc. And then the number of ways in which these in total N objects can be rearranged is this expression. And you could see this because for instance, we first arrange these n objects, considering they're all distinct. And that's n factorial ways. Then though, for example, we take there's n1 objects that are of a certain type. So then if n1 objects are in certain positions and n1 positions, then how they could actually be arranged. Different objects that are n1 can be arranged in those same n1 positions in n1 factorial ways, but they're actually all the same. So we should count them once instead of n1 factorial ways. So we divide. And similarly for the other, you also have to divide them too, because you only want to count them once. And then, since all of the indistinguishable objects are divided by to make sure that there's no overcount, then it's this answer. And actually, for combinations, you could see that that's a special type for grouping where r is equal to 2.
Wait, so how, for the grouping thing, how are we supposed to do like every one of these factorials?
Well, I mean, usually for these, we could look at a problem and we're not going to calculate it. The calculation usually won't be too hard. So it'll be mostly small numbers such as 2 factorial or 3 factorial. The denominator, for instance, we could look at this problem. And how many ways may we distribute 6 different books to Alex, Bob, and Catherine, such that each person gets 2 books?
Oh, so in this case, R is 2 and N is 6.
Exactly. Actually, R is 3, but N1 equals N2 equals N3, which each is 2, because each of these represent one person.
Wait, R is 3?
Yeah, because there's...
Is R the number of people?
Yeah.
Oh.
Because, okay, if we think of it like this, N is 6, which is the number of different books. Although all these books are different, but we could group them each type. For example, let's say N1 is the 2 books that go to Alex and they're the same type. Then N2 is how many the books that go to Bob, and N3 are the books that go to Catherine. So we group books, we consider them the same type if they go to the same person, because then if you, for instance, arrange them, maybe 1, 2, 3, 4, 5, these are books. 1, 2 go to Alex, but then if you arrange them as 2, 1, 3, 4, 5, 6, these 2 still go to Alex, so they are the same.
Wait, how do we solve this? Do we use a formula of N1 plus N2 plus and all the way?
Right. We could use this formula, and it's then would be 6 factorial over 2 factorial, 2 factorial, 2 factorial, which if you perform the math, you would get that it's 90.
I see. Wait, so like it only works when n is the same, or does it work when n is different? Like n1 is different from n2 and different from n2.
It also works if the n1 is different from other n's. For example, an A is different from NB. That also works. And we're gonna see an example using almost the exact same problem in our Kahoot. So now we're going to try a problem using water pipes. Using on the line segments given in the indicated direction, how many paths are there from A to B?
Can you make it a bit larger?
Sure. I'll just show you the picture.
How does this go with the groupings?
It's not really, sorry again. It's not really grouping, but it's just counting in general. But you could think of it in terms of grouping, like in terms of combination.
Wait, so like there's how many ways to this one, so like the I don't know how to, but the first grid thing to the right, one square to that point, that only has one way to get there. And also the one to the bottom, that also has one way to get there. And or if you go 2 squares to the right, they also have one way to get there. So are you just going to show each point how many ways you could get there?
Right. And I'll give you a hint how to find a formula for them. So each time could only go to the right or down. You may not go left nor backwards and nor up. So it's only right and down. And in all, you have to go right twice and down twice. So then think about how many steps exactly must you take and how you could think of a problem in terms of combinations or grouping or like arranging terms.
Okay. So can you tell me how to get that formula?
Sure. So if you left this, there are 4 terms in all. We could think about each arrow as a term. So there are 4 terms and there are 2 of the same type. So in all n, one could, or n in total is 4, and n plus right n right is 2, and down is also 2. So then this problem becomes how to arrange these terms. That's 4 factorial over 2 factorial times 2 factorial. And
so it's 24 over 4, 6.
Yeah, it's just 6. And that actually could also be thought of in terms of 4 choose 2. If you want to have 4 spaces for these 4 arrows to go, and if you want to choose 2 spaces for either the 2 right arrows or the 2 down arrows to go, that's also 6. Now we're gonna play some Kahoot.
Wait, after the Kahoot, is that it? Can you first give us some more practice problems for like this thing? Because I still don't really get the grouping thing.
Sure. I think we'll have time either now. Do you prefer to do more problems now or after the Kahoot?
Now.
Sure. I guess I could just make up some problems on the spot. So for grouping, let's say we'll have this word. And how many ways are there to arrange this word, to rearrange the letters? And Mississippi is also an arrangement, but another arrangement could be like I, S, 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 and P.
There is 4 I's and 4 S's. So do I have to divide it by 4 times 4 at the end?
That's the concept. You have to divide by some factorials after you get the numerator.
So the numerator is the number of letters, right?
Yeah.
Okay.
You don't have to calculate the exact number, but just to find the equation.
You forgot an extra I. No, like when you wrote the I, S, S, You forgot. It should be I, not I.
MISSI, SS.
No. Like you forgot a I. Like on the bottom, you wrote I, S, M, P. It's supposed to be 4 I's, not 3.
Right here, 4 I's in Mississippi.
Yeah, but then you added. But then you added a P.
Yeah, I think there should be 2 P's. My bad. Okay, so in all, yeah, there was quite some confusion on the number of letters, so I didn't spell it right. It seems there's 11 letters, I believe. So n is equal to 11. The numerator is 11 factorial. Then the denominator, let's say n1 is the number of i's, n2 is the number of s's, and 3 is the number of m's, and n4 is the number of p's. And then you have to make this denominator
Oh, I see now. Can you give one more example? And then we can do the code.
Sure. I think I should make this example with a bit easier, smaller numbers, so you could see exactly how it works. We do. Now there are 5 treats. And they'll be distributed to 3 kids. They're named J, L, and W. How many ways are there to distribute them such that J gets 2, L gets 2, and W gets 1?
Wait, I'm not sure what I should do if like, wait, oh.
This problem is actually similar to the one we saw here with these 3 kids.
Wait, is the formula 5 factorial over 2 factorial times 2 factorial times 1 factorial?
Correct. As you see, each type, that means 2 trees are of the same type if they go to the same person. So if you have, let's label the treats 1 through 5. And for instance, if you make it like this, that can be a way where J gets 1, 2, L gets 3 and 4, and W gets 5. But there's actually 4 ways to permute these numbers where you get the same grouping. So if we do 2, 1, 3, 4, 5, or 1, 2, 4, 3, 5, or even I go up 2, 1, 4, 3, 5. That's all the same grouping, although there's 4 different ways. Because each of these 2, we could permute them in 2 factorial or 2 ways. So that's why if you divide them by 2 factorial times 2 factorial. Are you guys ready to move on to the Kahoot?
I think so.
Okay. Okay. We so far just have 2 participants. I'll wait 1 more minute before we start. Okay. We're going to start. Okay. So this problem is similar to the Mississippi one. There are in all 7 letters. There are 2 I's and 2 A's and 2 N's. Then there's 1 D. So then it's 7 factorial over 2 factorial times 2 factorial times 2 factorial times 1 factorial, which is 630. And by the way, a palindrome, I think you've heard. So it's basically a number that's the same forward and backwards. For example, 101. And by 3-digit, I mean, oh, we're already there. So good job. So basically, we're finding 3-digit palindromes. So it's of the form ABA. And the leading term can't be 0, so it has to be between 1 and 9. While B is between 0 and 10 as integers. So then, as you can see, there are 9 ways to choose A and 10 ways to choose B to make such palindromes, because then if you choose the first 2 digits, last is also chosen as A. Good job, Yo-Yo. This question is a review. Okay. So for this problem, a terminating decimal is one that has a decimal part that does not go forever having non-zero digits. So that means, for example, 125 is a terminating decimal because then beta will always be 0 forever. But example of non-terminating decimals, for example, 333, so on, it always goes 3. And terminating decimals are terminating if and only if the fractional representation of it has a denominator that only consists of factors of 2 and 5. Therefore, if we want to find such a positive integer that has a terminating decimal representation, let's say b, then the fraction is 1 over b, which has to be 1 over 2 to the power of x times 5 to the power of y. And then what we can do is count how many are there for positive integers less than 100. That we could do casework on the power of y. So if y is 0, then we could do, for example, x is 0, 2, that's 1. X is 1, there's 2, all the way to 64, just x is equal to 6. Then so on. If you do the casework, in this case, it'll be 5, 10, 50. And then 25. And actually 5, 10 here, 5, 10, 20.
Wait, I have a question.
Go ahead.
You said positive integers less than 100 have reciprocals with terminating decimal representations. Does that count multiples of 2, like 4, 2, 8, so on?
Yeah, definitely. It's here. That's multiples of 2.
So there's 64 numbers?
No, it's 1, 2, and then 4. In all, there's 7 from 0 to 6, because there's 1, 2, 4, 8, 16, 32, 64.
Wait, so for multiples of 2 that have, that consists of 7, 3, 9, and other prime numbers, do they all not work? Except for 5.
Sorry, can you please repeat?
So numbers such that consist 3, 9, 7, 11, and 13, all those type of numbers, do they all not work for this thing?
Yeah, they don't work because, for example, 3, its prime factorization is just 3, but that doesn't consist of just factors of 2 and 5 since it has 3. Another that does not work, for example, 6, because that's 2 times 3. And the denominator can have 3.
Okay.
Yeah, and I want go over more counting just quickly. And all, if you add them up, it'll be 15. It's just satisfying.
Okay, so you just have to find all the numbers that work.
Yeah.
Oh, thank you.
No problem. Huh. Good job. Good job, Yo-Yo. Okay, good job, Jessica and Yo-Yo, and all the girls who participated. I hope that you found today's class fun, and the homework will be posted soon. And there is a problem that I didn't post. I won't post to answer because there's the solution, but it's for you to read through their solution. And then there's also the last two problems, which are quite challenging. So you could just try your best on them, and we'll go over them next class.
What type of problems are those last two numbers?
They also involve permutations and combinations, but they're similar. One is similar to the water pipes question we did, and another is about rectangles and how you could use combinations to solve it.
Okay. So, are they like challenge problems?
They're quite challenging, yes.
So are they sort of connected with the problems we did before?